All right, do the students hear me properly?
Yes.
Okay, great. So let me just ask if, some of you randomly, from one course to the other, I'm not asking each of you to do it for every lecture, could just, put on their camera, because to be honest, it's a bit difficult to teach in front of a black screen. I would find it a bit more nice for myself, and probably for you also, to show yourself some time, and this way it will be a bit more interactive. Of course, the next lecture, then you can disappear behind your camera, no problem, and I would ask some other students to show themselves if that's possible. At least I have the impression to talk with someone. Is that okay for everyone? Okay. Also, I would kindly request you to be a bit responsive when I'm asking questions. Otherwise, it will be very hard for me to gauge whether what I'm saying is clear, too fast, too simple. So just tell me as we move on. All right. So let me just say a few things. So I was not supposed to teach that lecture, so let me just put my thoughts, let me structure my thoughts. Okay, so let me mention something. Do not stress too much about taking a lot of notes for that course, okay? In the sense that for me, it is important that you follow what I'm saying as it goes on, okay? Because I have written very detailed notes that will contain essentially everything I'm going to say, okay? And slightly more. So instead of trying to write down everything I'm saying while listening, I would recommend to just focus and ask questions live, and then I will send you the notes later in the day that will need to be slightly updated later, but at the end you will have a full document containing everything, okay? Perfect. So we're going to start with the main question, okay? So this course will contain concepts and techniques from different things, okay? The first one is, as the name says, it's information theory. Can you read properly? Okay, I will assume so. The second one will be statistical mechanics. So I assume this is a field where you're less familiar with, because if I understood correctly, most of you are not physicists. My background is theoretical physics. I moved to information theory and statistics later on, but we will see that it's very much connected, of course. And the third field toolbox we're going to use is random matrix theory. Okay. So I will give introductions, self-contained introductions to all of these fields, okay? And all that are going to be used to study inference problems in the language, or in the framework, let's say, of Bayesian inference. So I'm pretty sure that most of you already have some knowledge about what Bayesian inference is, but I will recall some basic concepts. Okay, but first of all, what is the main goal of the course? Okay, the main goal will be to study one specific instance of a high-dimensional problem, because I will argue that even if we're going to focus on this specific model, most of the things we're going to say generalize to a very broad class of high-dimensional inference problems, okay? So do not imagine that what I'm going to say is very specific. That's rather the opposite. But I think that from the pedagogical point of view, it is important to fully solve, fully dissect one single model. And this is what we're going to do, especially that we have a finite amount of time. We have just 1 week. So I think it is better to focus on that single one. But you will be able to use all these techniques and ideas in a much broader context. So the model we're going to use, let me just quickly state it, is called the Spike-Bigner model, and this is a matrix inference problem where you measure y equal tau, which is a scalar, times a rank 1 matrix plus z. Okay, so think of y as some data. Tau is a so-called signal-to-noise ratio. This is a scalar. And x, which is a vector in Rn, is the piece of information we want to recover. So XX transpose is a matrix of rank equal to 1. And z is the noise. Y is the data. And given this data, you wish to ask, so sorry, Jaspal, there are people that keep entering the room. Could you please take care of administrating this, because it's a bit difficult to teach while accepting all these people. Thank you very much. So the question we're going to ask is, given this data, are we able to reconstruct this rank 1 matrix? And we will see that it looks very special, this model, but it has tons of applications, and I will show you that later. Okay, but at the moment, let's just assume this model is interesting. So the first question that we're going to ask is really an information theory question, IT. Can the signal XX transpose, this rank 1 matrix, be recovered given the data y? Okay, and by can here I really mean we do not care about how costly it is for a computer. This is really an information theoretic question. Is there simply enough information in the data y to say something meaningful about this rank 1 matrix? Okay, so this is the first question, and this is where really information theory and statistical mechanics will be important. And random matrix theory as well, we'll see. And the second question, which is more an algorithmic question, an engineering question, if you wish, is can it be recovered at low computational cost? That is, efficiently. Okay, because it's very nice if you can prove that there is information in the data and therefore in theory you should be able to recover it. But if it takes the age of the universe for the best supercomputer on Earth to recover it, it's not a very useful result, right? The more useful result is one that says that indeed there is enough information, but also we can provide efficient algorithms that extract it in a reasonable amount of time. Okay, so we're going to study these two questions, but the first we need to study is whether it's possible, information theoretically. And then at the end of the course, I will show you how to extract this information in the best possible way and being efficient. And we will see a bit earlier in the course, actually tomorrow, how to do that with another algorithm, which is much simpler, but which is suboptimal. We will see. All right, so this was for the introduction. So let's now go to lecture 1, which is about Bayesian inference. Okay, so let me also mention right away that I will be a bit loose with the notations. I will not track what are matrices or vectors. I will say it orally, but you should be careful with this. The notations are well explained then in the notes. Again, you will have them later today, don't worry. you will be able to follow the notes in live. But if at some point you miss something, if the notation is not clear, just stop me. It's probably because I haven't defined it properly. Okay, I won't have time to be so precise with all the notation, otherwise we won't go through the course. So just stop me when something is not clear. So let me remind you the basics of Bayesian inference. Is y a parameterized function of x? So y is a function of x, yes, because you see this data there depends on x through this relation. So it's x transpose plus z. So yes, y is a function of x. The data is a function of the signal. Thank you for the question.
So, do we want to estimate x as a value, or we want to estimate the functional form? It's the I did not understand the.
No. This is a particular matrix. This is a matrix of numbers, and we want to evaluate these actual numbers. Okay, not just the functional form. We're going to assume that we know the functional form, in the sense that we know that y depends on x in this way, but we don't know what this noise is. We don't know the actual realization of this x, and we want to recover the xx. Okay?
Thank you, sir.
Thank you. Perfect. So in Bayesian inference, we have three main ingredients. The first is the prior, p of x. So I will always use the notation x for the unknown parameters, the information to recover. Y will be used for the data. Okay. So the prior represents any a priori information you may have about the signal before observing the data. Okay. The second ingredient is the likelihood. So the likelihood is the probability distribution of observing some data y given x. Let me mention here that what I'm saying is not specific to the model I defined before. What I'm saying now is completely general. Okay, y and x can be anything. Okay, they don't have to have the same dimension. X can be a tensor, it can be anything, y can be anything. Okay, this is completely general. So the likelihood is the probability distribution. It's a conditional distribution that models the data generating process. It is your model of how the data y was generated if the unknown parameters were taking the value x. Okay. And from these two ingredients, you can construct the main object of interest in Bayesian inference, which is the posterior distribution. So the posterior distribution is the law of x given y, which is given by Bayes' law as the product of the prior times the likelihood divided by the normalization. And this normalization, of course, you can write this as the joint law of x and y. This is the product rule. Okay, this is by definition of what the conditional distribution is. And so if you are integrating the joint law of x and y with respect to x, this normalization is just p of y. That we call the evidence. This is the evidence in the Bayesian language. Okay? So I'm sure that these are known things. So let's move on. Let me evaluate the time. Jaspal, can you tell me until what time can I teach? Can I take slightly more than what was expected, given that we started later? I will assume so.
Am I audible?
Yes.
Sir, we have half an hour more. We can, because we started late, so we can cover maybe 30-40 minutes more. What all we have planned for lecture 1, we can cover.
Yes, this will be a bit difficult to finish in half an hour, but okay, let me...
We can take 40 minutes, what all you require, we can take.
Okay. So maybe what I can do is maybe just open the notes I've written and go through them with you. Yes, because otherwise I think it will be too long. So
yes, I shared slides with you, so maybe you can we can cover from that.
But I will simply so because otherwise we won't be on time given the delay.
Yes.
So let me give me 1 second. Yes. Yes. Excuse me, everyone. This is it seems to be a constant in the scientific world. Every first lecture, there are problems. This is unavoidable, but we should be okay. Perfect. So do you see the notes? So basically, these are the notes I'm going to share with you. So let's try something. I will go through the note. Don't read all the sentences. Just focus on what I'm showing. Okay. And let's see if the pace is slow enough so that you can follow. If you cannot follow, please stop me. I will say much less things, and I will just give you the note later on. And all right. So that was the motivation. Okay. This is not. I don't like the way it's shared. Excuse me. I will. Okay, that will be fine. Okay, so that was the model, right? So let's go to where we were. Maybe it will be actually easier because the notations will be more clear. So we are here. So the Bayesian posterior is the following. This is the law of the unknown parameters x given the data y. And as I said, it is the product of the likelihood distribution times the prior, which is then correctly normalized. And this normalization is called the evidence. Okay, so this is very simple, basic problem. So let's consider one example. Here, example 2. Let's say that you have you are a statistician trying to evaluate the distribution of the heights of people in a population. Okay, so what you could do is assume, let's say from statistics from other countries, what is the typical height of people, okay, in the world, let's say, for, let's say, males of a certain age, and what is the standard deviation of this height, okay? And so you would have some prior given by the statistics, which is that the expected height of a human in the world is 1.70 meters. The standard deviation, the variance of it is 25. And so your prior is a Gaussian distribution with this mean and this variance. Then you would sample the distribution to get some data specific to your country, India. And you would realize that the empirical average, the average you compute over these samples, is actually bigger. It would be this mu bar, which is 175, obtained from, let's say, 10 samples. And the variance you would observe is bigger than the one you assumed in your prior. It would be 49 centimeters. So this is your data, okay? And Bayes' theorem tells you how to combine your prior and the data. And if you do the computation correctly, you realize that the random variable corresponding to the height given now the data, so you are updating your knowledge about this random variable by combining your prior and the data, you would obtain some formula here, which I won't explain. This is very simple, actually. This is an exercise to try. And you would realize that the posterior distribution of this height is now updated, and the mean is not anymore the prior one, is not anymore 170. It's closer to what you observed in the population. It's 174, and the variance would be, I think there is a typo here, it's 41, okay, and not 4.1. So you have updated your belief in a principled way, and now you have a better, more reliable description of the distribution of the height in the population. Okay, so very simple example. So this notation means the random variable corresponding to the unknown, in this case the height, conditional on having observed the data y. Okay. Bold variables will be used for vectors and matrices, while without bold, normal letters will be for scalar random variables. Okay. Perfect. So now that we have a tool, a way to obtain probability distribution of random variables which combine our prior information, our prior knowledge, together with data. This is the posterior distribution given by Bayes' rule. A meaningful question is how to use this probability distribution to take a decision. So making a decision means estimating, choosing a value for the unknown parameters. Now we have a distribution. How do you pick the value for this unknown parameter? So this is done using what we call Bayesian decision theory, which goes as follows. So the first main ingredient in Bayesian decision theory is a notion of goodness. So how to quantify whether a decision is good or not. And this is done thanks to the so-called loss function, which depends on the unknown parameters x and on your decision. Think of this delta as an estimator for the unknown parameters x. Okay, so this function is the cost of choosing the decision delta when the true parameters is x. But of course, the problem is that you do not know x. Okay, that's the whole point. You are trying to estimate x. Okay, so you do not have access to the loss function defined in this way. Okay, because this x is unknown. Okay, so the way to define a meaningful question that you can actually compute from the data is the so-called risk. The risk is the expectation of the loss given the data. Okay, so you see now the risk, which becomes a function of your decision and of y, not anymore of x, of y, and y you have it in your hand. It's the data. So you can compute a function of this form. This is meaningful. It only depends on things that you can control, the data and your decision. And by definition, the risk is the expectation with respect to the posterior distribution of the unknown parameters given the data of the loss. Okay? So you are averaging the loss with respect to the unknown parameters using your best guess of what the distribution of these unknown parameters is, which is, of course, the Bayesian posterior distribution. Okay? So now we have a meaningful quantity that we compute. This is the risk, which is the average loss, the posterior average loss. Okay? And what we call an optimal decision, okay? An optimal decision is given by definition as the minimizer of the risk. Okay? So
optimal decision.
Yes, was there a question?
No, I was getting sorry for interruption.
No problem, no problem. So again, I repeat, everyone, you can stop me whenever you want. By the way, I think that I will do like this and follow the notes because otherwise I won't make it on time. It's a bit difficult to write on the iPad. At the Blackboard, it's a bit easier. Is the pace okay? Are you able to follow when I speak like this on the notes?
It's a bit fast, but we can grab.
It's a bit fast. I will slightly slow down. Okay. Thank you. So now that we have this risk function, which quantifies how good a decision, which means an estimator for the unknown parameters, is, and that depends on our observed data, so it's something we can compute. The optimal choice is, of course, the one that minimizes this risk. And this is what we call a Bayesian optimal decision. Okay? And we denote it by this delta star. The star here would mean optimal. And this is only a function of the data, as it should, because it's the only thing that you have in your hands, the only thing you can observe. Okay? So let's look at an example. If we take for a loss the L2 distance, so the Euclidean distance between the unknown parameters that, let's say it's a vector, between the vector of parameters and our estimator of it, delta, what is the optimal decision one can take? So let's just use the definition and compute. So I take my loss here, and I'm averaging this loss with respect to the posterior distribution. This is what this notation means here, okay? So this notation, expectation of something conditional on y, really is the same notation as the expectation with respect to x given y, which is really an integration with respect to x of p of x given y of the something. Okay, so this is an expectation with respect to the posterior. Okay, so here, this notation is here to remind us that we're conditioning on the data. So it means the data is given to you, and therefore we are talking about the posterior distribution. Okay, so I'm computing the average of my loss, my Euclidean distance in this case, with respect to the posterior distribution. So I can just do very simple manipulations here. I can develop my square here, and I obtain three terms. The first term comes from the norm of x, which does not depend on my decision. So this is just a constant. I can forget this term. This is a constant with respect to delta, which is the object I want to focus on right now. The two terms that depend on delta are here. Okay, we have the norm squared of delta, and the inner product, this point here means the standard inner product, between my delta and what appears to be the posterior mean. Okay, so this notation there is the mean of my unknown parameters with respect to the posterior distribution. Okay. Okay, and I can solve this equation. So this loss, by the way, this is an Euclidean distance, this is a square, so it's like a parabola. It's a convex function. So if I'm looking for the minimum, a convex function has a unique minimum. So I can just look for the decision that minimizes this convex function by looking at where the gradient cancels. Okay? So I'm taking the gradient of what I just wrote with respect to my decision, which is a vector equal to 0. And what you obtain is this equation there. Very simple. And you solve it, of course, and it gives trivially the following. So the optimal decision when you consider the Euclidean distance as your notion of loss, as your loss function, is the posterior mean. Okay? So this is what we call the Bayes estimator. Okay? So it tells us that when we consider Euclidean distance as a notion of how good an estimator is for a given unknown, we are trying to minimize the Euclidean distance between the two. Given only the data, the best we can do, the very best we can do, is to compute the expectation, the mean of the posterior distribution. Okay? This is the Bayes optimal estimator. Let's consider, so we call it also the minimum mean squared estimator, or MMSE estimator. Simply because this Euclidean distance is also called the mean square error. Okay? And we are minimizing the mean square error. Okay, so this is the best possible estimator in this sense. So, let's consider another example. Let's now take the loss to be the so-called 0-1 loss. So it's a loss which is 1 if your estimator is not exactly equal to the unknown, and it's 0 otherwise. Okay? So you are forcing your estimator, you're only happy when you recover exactly the unknowns. So this is a meaningful loss only in the case where these unknowns are discrete. Otherwise, you cannot reconstruct perfectly real valued numbers. Only discrete numbers can be reconstructed perfectly. So for discrete random vectors, let's say, we can consider this loss, and we do the same exercise. We compute the risk associated with it, which is the expected loss. And what you get is simply 1 minus the probability distribution of a given decision with respect to the posterior distribution. So you can try, maybe you don't see it right now, but this is very simple. You plug this definition of loss, where this 1 is the indicator function. It's 1 only if this event is verified there, and it's 0 otherwise. Okay? So you plug this here, and you will realize that what I have written here is correct. And in this case, how do you minimize this risk? You see, you want to, because there is a minus here, you want to maximize this probability, okay, in order to minimize this risk. And therefore, the base optimal estimator in this case is, so what's the best decision you can do is to maximize the posterior distribution, is to take the argument that maximizes the posterior distribution, the argmax. And we call this the maximum a posteriori estimator for obvious reason. Okay? I hope this was clear. So this was a short introduction to Bayesian decision theory. So now we have essentially a framework to understand how to pick an optimal decision, how to pick an optimal estimator for unknown parameters when we are able to write down the posterior distribution according to Bayes' rule. Okay? Perfect. So, again, do not read everything that appears at the screen, just focus on what I'm pointing at you, okay? So now the question is, why is the Bayesian framework important, especially when we go towards high dimensions? And remember that this course is really about inference in very high dimension. We're not interested in reconstructing unknowns, which are, let's say, just scalars or 2 or 3 numbers, okay? This is the statistics from the past. So classical statistics from the 19th century and for the past 100 years, people were interested in settings where basically you have lots of data and you are trying to infer few unknowns. So, for example, you could do experiments. You were Newton and you are throwing some balls and you are recording the trajectories of the balls, and the unknown parameter you want to infer is the gravitational constant. This is just one number and you can measure tons and tons of trajectories. So this is classical statistics. Lots of data and few unknowns. This is not what we are interested in this course. What we want to study is high dimensional inference. The difference is that you still have lots of data, but you as well have lots of unknown parameters, and their numbers is essentially comparable, okay? And this is where really new phenomena and interesting things that we're going to see happen. This is what we call high dimensions, okay? So again, if I denote by X the unknowns and Y the data, let's think of them as vectors at the moment, the dimension of the unknown, P, is proportional to or much greater than the number of data N. Okay? So this is really the high dimensional world. Okay? And when you are in high dimension, in particular, the tools from classical statistics, what people were using in the 19th century, they fail. And one of these tools is called maximum likelihood estimation. Okay, this is the weapon of choice to use if you are in the classical regime. The classical regime, contrary to this, means the number of unknowns is much smaller than the number of data. So this is the classical statistics. when you are doing classical statistics, you can show that actually the best to do to make a decision to estimate the x is maximum likelihood estimation. What does it mean? It means to choose XMLE. So this is our optimal decision. When we have lots of data, you can show this. This is the maximizer of the likelihood. Okay? So you do not need any prior. You can just take the likelihood, which is the conditional law of the data given the unknowns, and maximize it. You see, this is different from the maximum a posteriori estimator that I defined just above. The maximum a posteriori estimator includes your prior information, which is very important when you are in high dimensions, because I will explain now. But in high dimensions, you need prior information to make inference. Instead, in low dimensions, so in the sense of classical statistics, lots of data compared to few parameters, just using the maximum likelihood estimator is optimal. Okay, but this is not the case anymore in high dimension. In particular, if you take this kind of decisions in high dimension, you will induce overfitting. You will tend to essentially reconstruct things that are related to the noise rather than the signal. Okay? Okay. Perfect. So let me see where we are time-wise.
Professor, if you wish to, we can cover curves of dimensionality in the next lecture after lunch. It is as per your choice.
Yeah, I mean, I need to say quite a few things after lunch as well, but this, if...
okay, you can take maybe, if you wanted to cover, we can cover.
Maybe I can take 7 minutes. I won't need more. Okay? So let me discuss a very important notion, which is the curse of dimensionality. The curse of dimensionality is precisely the reason, let's say the concept behind, let's say a set of phenomena that imply that classical statistics tools, such as maximum likelihood estimation, fail when you go in high dimensions. Okay? You need to rethink statistics when you go to high dimension. And the reason is a set of phenomena actually that we put in a bag, a conceptual bag that we call the curse of dimensionality. So it can mean many different things, and I will just show you a few of these phenomena that basically say that when you go towards high dimensional spaces, making inferences in high dimensional spaces, everything changes compared to the low dimensional world where you evaluate low dimensional quantities, like the gravitational constant, just one number. What happens when you evaluate very high dimensional vectors? Everything changes. This is what we mean by the curse of dimensionality. Okay? So, in particular, when you go towards high dimension, one of the key problems is that you can never fill the data space. So what do I mean by this? What I mean by this is the following. Imagine that you are trying to evaluate just a real number. So the true parameter is this value there in blue. Okay? And what you are measuring are, let's say, noisy observations of this true value. Okay? So this noisy observation, this data, are points that are somewhere there. Okay, some are far, many are a bit close to this point. Okay. So you see that basically the more I give you data, the more I fill this space. Okay? And let's assume that this space is just 0, 1. Okay? You see that if I want to be sure, let's assume that these points are sampled in a manner, and I want to be sure that I have enough points to be close enough to the truth, like this, with a certain precision. You see that the precision that I get, this delta x, let's say, between 2 points, the typical distance between 2 of my points, goes as 1 over the number of data. So I can quickly fill the space somehow. It means that distances between points, between data points, tend to go to 0 as the inverse of the number of data, okay, in 1D. But now, if you go to 2D, 3D, 4D, 100 dimensions, you need more and more and more data because you are not filling just anymore a line. You are filling a hypercube, if you want. So very high dimensional space. So imagine that you want a precision, a resolution, meaning that you want that the typical distance delta x between 2 points in your space. Let's assume we sample the points uniformly, just to simplify, okay? We're sampling the points uniformly. We want the resolution to be 10 minus 2. In one-dimensional space, the number of points you will need to have such a resolution is 100, okay? Because if you put 100 uniform points on a line between 0 and 1, the typical distance between them will be 1 over 100. But now if you want to have the same resolution in the sense of having points which are that close to each other in this space, when the number of dimension is now 10, 100, sorry. So high dimension, even if it's not so high, will be 100 to the 10, which is 10 to the 20. So you see, you need exponentially many more points to fill the space, okay? But of course, you never have access to that many points, okay? So what does it mean, these very simple examples of filling points uniformly in a space? It means that in high dimensions, if your unknown parameters live in high dimensions, you will never have data which are close to each other in this. You will never have, like, think of this data as kind of noisy observations of these unknown parameters. These noisy observations will typically be very scarce, very sparse in this space. They will not fill the space properly. Even if you have 10 million or 10 to the 6, which seems to be a big number, data, this is really vanishingly small compared to what you would need to have such a small resolution. So in high dimension, you always need so much points to fill the space that never happens, okay? So this is what we call the exponential sample requirement. So data in high dimension is very sparse and points are very far apart, okay? Another property of high dimensional spaces is the dominance of boundaries. So this is another weird property in high dimension, which can be exemplified by the simple formula. If you take a d-dimensional sphere, okay, so you just take the formula of a sphere in d dimension, and you compare the volume of a shell which is at the boundary. So this is the volume of the shell between r minus epsilon and r for a small epsilon. You compare that to the total volume of the sphere, and you see that it goes to 1 if the dimension goes to infinity with this formula. So this is a very simple exercise. You should show it. This is just volumes of sphere. So what does it mean? It means that if you put any point at the center of a ball in a high dimensional space, most of the volume, most of the points can only lie very close to the boundary of the ball. Okay, they cannot fill the space in the middle because most of the volume is actually contained very far away from the center. Okay, so the picture that you have in mind of a ball in 3D is very wrong in high dimension. In high dimension, a ball does not look like a ball like you imagine. It's a very weird object where most of the volume is contained close to the boundary of the center. Okay, it's really compressed at the boundary. And so this in particular implies that every points in high dimension are very far away from each others. Okay? So it implies in particular that naive algorithms will fail in high dimensions. So let's people are still joining. So let's consider the following classification problem. Assume that the space is again the hypercube 0, 1 to the d, and you have 1,000 data points, which are sampled uniformly in the space. Okay? And the classification problem is the following. The label associated with a point, if you want the color of a point, every point in this hypercube can take one of two colors. It is 1, meaning white, if the sum of its components is greater than the dimension over 2, and it is 0, meaning black, otherwise. So we have these black and white points in this very high dimensional space. And this is our data. And now, of course, you do not know this rule. The inference problem or the learning problem, here this is the same, is to understand what this rule is given the data only, given the observations of these black and white points. Okay? And the naive algorithm that works very well when you are in low dimension, but fails when you are in high dimension is the following. It's called one nearest neighbor algorithm. This is an instance of the KNN algorithm in general, the K nearest neighbor algorithm. So what you do is very simple. So imagine that now you have a new point, the color of which you do not know. So you want to guess whether this point should be classified as black or white, given the observations of many black and white points, 1,000 of them. So what you could do, because again, this rule is unknown, is the following, is just to pick the nearest neighbor of these points of unknown class and say that the class for this unknown should be the one corresponding to its nearest neighbor. Okay, it's a very simple classification rule. But if you do so, it will quickly fail as you increase the number of dimensions. If you go from d equal 2 to 200 to 2000, it will fail. Why? Because you can compute, you can just do a simple simulation, you will realize that the mean, the average distance between any 2 points in this space, like grows as the dimension grow, okay? But at the same time, the nearest neighbor of any point distance also grows. So basically, you can take any point in this space, there are many other points, and you compute the average point with respect to them, and you can also compare that to the distance with the nearest neighbor. And you see that these two distances in low dimension, they are very different when d is equal to 2, but in high dimension, they are very close to each other. What does it mean? It means that there is no more notion of local neighborhood. It makes no sense to compare a point to its closest neighbor because it is essentially at the same distance than any other points. Okay? This is again related to the fact that if you think of this unknown point at the center of a ball, all the remaining volume is at the boundary of a sphere around it, okay? Of this high dimensional sphere. And so it makes no sense to make decisions based on notions of distances, because notion of distance loses meaning in high dimension. Okay? Does it make sense what I'm saying?
Yes.
Okay. Thank you for being present, by the way. I don't know your name, but I'm happy to see your face.
Arpita.
Nice
My
to
name
meet
is
you.
Arpita. Same here.
All right. So like I said, in high dimension, distances become uninformative, and many naive algorithms are based in low dimension on comparing distances. So you cannot do that anymore in high dimension. The data concentrates in boundary regions. Remember these examples of the sphere. And notions of local neighborhoods disappear. There is no more neighborhood. In high dimension, every point is extremely far away from any other point. And this is a big problem. This is the curse of dimensionality. Okay? So the way to fight against the curse of dimensionality is by making assumptions. And this is why Bayesian inference becomes so important. Okay? Bayesian inference is about combining the data with assumptions in order to make better inferences. And assumptions in high dimension become absolutely crucial because of the curse of dimensionality. So there are different types of assumptions you can make, and there are tons of techniques to do different type of assumptions. So one thing you can do always, which is a sort of assumption, which is dimensionality reduction. You can say, okay, it's too difficult to work in high dimensional spaces because points have no neighborhood, distances make no sense. What I can do is to reduce the dimensionality. I can project back my high dimensional data to low dimension, and this is done through different techniques. One is called principal component analysis, and we're going to study it in detail. This is very much related to this course. But here you're making an assumption somehow. So it's a Bayesian procedure as well, because you're making the assumption that there exists a meaningful subspace of this high dimensional space on which I can project my high dimensional data without losing all the information. Okay? So there is some specific low dimensional projections that make sense to consider, which is a prior. Because what is this low dimensional subspace? You're making an assumption that it exists and you can find it, and the way you find it is somehow can be thought as a prior in the Bayesian context. Another thing you can do is called feature selection. Okay, so feature selection is about saying, okay, my data lives in very high dimension, but probably many of its, let's think of this as a vector. My data are samples of a vector. Many of its components should not matter too much, should not be very relevant for the task, for my inference task. So maybe I can somehow just select what are the features, what are the components of my vector that do matter to make inference. It's again a type of dimensionality reduction. You're reducing the dimension, and you can do that based on different techniques, based on in particular, what we call the lasso, which is a prior that says that basically most components do not matter and can be set to zero. So like if you have data living in high dimensions, what you do is to say all the components that are sufficiently close to zero, I just set them to zero. Okay, and the only relevant ones are the non-zero ones. And so doing so, you can shrink the dimension of your vector and make the inference easier. Okay, and you can use regularization. Regularization is another type of prior. For example, you can assume that the unknown parameters have a norm which cannot be too high. So this kind of things. Okay. So all these techniques can be seen as different forms of priors in the Bayesian language. Okay. All right. So let me stop there. And we're going to continue a bit later by introducing the basics of information theory.
Sir, I have a quick question.
Yes, please go ahead.
On the distance part, like when you mentioned that the mean distance grows as dimensionality decreases, this was the intuitive part for me, because I thought that sampling algorithm prefers faraway things, but when we went to the mean nearest neighbor distance, this was the less intuitive part for me. that even the nearest neighbors, because even in high dimensional spaces, we could sample just a one distance away thing. So why is the mean nearest neighbor distance increasing as dimensionality increases? This is something I'm not able to wrap my head around.
Okay, so the sound quality was not really good. So let me see if I understood. Your question is essentially is why is this mean distance between points increasing with the dimension? And why is this?
Yeah, I'm sorry for this one. What I wanted to say was the main distance. I think this increases because of the sampling thing, because most of the points are at the boundaries. Then we're anyway sampling points far away. But the mean nearest neighbor distance thing, this is something that is very non-intuitive for me.
Yes. Okay.
Like, why is it increasing?
Yes. So your question is, so the mean distance is increasing with the dimension, but why is that so that also the typical smallest distance between points increase with the dimension, right?
Yes, sir.
So, yes. So imagine again consider again this formula. This formula is telling us that if you take a ball in high dimension, most of the volume is close to the boundary. So imagine that now you are sampling, so you place yourself at the center of such a ball, and you are sampling random points in this ball. Okay? Let's say 1,000. Because quasi all the volume is contained at the boundary, it means that almost all these 1,000 points will be close to the boundary. You have because the chance to be anywhere in this ball is proportional to the volume of this subvolume, right? So you have a full ball and you take a small subset of this ball. What is the chance to sample a point here? It is related to the volume of this ball divided by the total volume, right? But
yes, sir.
The total volume inside the ball is going to 0 in high dimension because all the volume is dominated by the boundary. So it means that if you sample points uniformly randomly in this ball, the chance to fall close to the center is going to 0 with the dimension because there is no volume. And in particular, the closest point will be far away. Yes.
So wouldn't there always be a point? Let's say I have an n-dimensional vector. I can just perturb one dimension of it just by one and find the closest neighbor at one in each of the dimension.
I'm sorry, I do not hear well enough your question. I don't know if it comes from my side or if the others hear you properly. But
maybe you can write the question in the chat. That would help. Your voice is breaking.
I understood, ma'am. Yes, ma'am. I will write it up in chat. Thank you, ma'am.
Okay. If the question was not properly answered, please send it in the chat and I will try to answer. Okay. All right. So, are there any other questions by the others?
Hello, very good afternoon, sir.
Hello.
Am I audible?
Yes, you are.
Okay, so my question is like what you told about d-sphere, for example, and if my question is if there is a zero from 0 dimension to the infinite or the d dimension hypercube or whatever it is, like in a matrix, it is for hypothetically, like if we start with a 0 dimension point data set to the 1,000, 2,000 and to the infinity, then does it is it like comparable for each data sets will be comparable for the same distance concentration function or and boundary dominance?
No, of course no. So what I said here was specific, somehow specific to the the simplest setting where you just assume that points that we call the data points are sampled uniformly at random in high dimension, okay? But of course, in reality, for real data sets, points are not sampled uniformly. If you consider, I don't know, if your data set is made of images of dogs, these are very structured data, right? So these are not uniform points. So you can think of an image of a dog as a vector where every component indicates the value of a pixel, let's say black and white, okay, to simplify. So this is a very high dimensional vector. And of course, the pictures, like if you think of all the possible pictures of dogs, they do not fill uniformly the 0,1D space. So let's say D, here is the number of pixels. And of course, the set of images of dogs is not filling this space, okay? It lives on what we call a lower dimensional manifold. It is a subspace of 0,1 to the D, okay? But it's still a high dimensional space in itself, okay? But so it means two things. It means that this curse of dimensionality is there if you make no assumption about the data. So if you know nothing about the data, the best you can assume is that it is sampled uniquely in the space. And therefore, you have this issue of the curse of dimensionality. But now, if you assume something about the data, in particular that it lives on a smaller subset of the whole space, it's called the lower dimensional manifold, then maybe you can make inference and learning easier. And this is what machine learning algorithms and Bayesian algorithms do. They somehow try to learn to understand what is this lower dimensional subspace that matter, okay? So in the Bayesian language, if you assume that your data is structured, you could do this. You could assume that it is not true that all the values of all the pixels matter and can take any value. This is not the case for images of dogs, for example. So somehow they should be a better representation for the data. They should be a lower space in which the data lives. It does not fill the space completely. And this is what we are trying to learn when we do, excuse me, where did I mention this? Yes, so techniques of dimensionality reduction. Oops, what is happening? Techniques of dimensionality reduction or feature selection, they're trying precisely to encode this prior information in the model that the data should not fill the space uniformly, that it should live in a subpart of the space. But then you need to learn what this space is. But simply the fact of assuming that there is such a lower dimensional space will help you to make inference. So this is a prior, a very important prior. But nevertheless, so what I'm saying is that you can fight against the curse of dimensionality by making prior assumptions, such as the fact that the data is structured in a certain way. Does it answer your question?
Yeah, okay, sir, thank you.
Okay, so may I request everyone to kindly switch on their camera? We will take one screenshot for this lecture. So may I request everyone who are there, may please online, may please switch on their camera. Am I audible?
Yes.
Yes, okay. So we will take one screenshot and then we will break and then we will have another lecture at around 2:40, maybe 10 minutes later, as Professor Barbier says. Sir, what time we have to rejoin at?
We rejoin whenever you want, Jasper.
Okay, 2:40 as planned.
As planned.
Or if you want to delay, we can delay 15 minutes because this lecture has extended already half an hour.
No, but 2:40 it means almost in an hour and a half. That's more than enough.
That's more than enough. Okay. So we will go as per scheduled time, that is 2:40 p.m. after lunch. So may I request everyone to kindly switch on their camera. We will take one screenshot and then we will leave this session.
So we'll stop sharing. Let me stop sharing.
Okay. Yes. Now we can see everyone. Okay. Yes. Perfect. So maybe we take some screenshots. Okay.
GIM course. Course.
Okay,
right.
Thank you. I thank everyone to join. So maybe we all will rejoin at 2:40 p.m. now. Thank you everyone to join, and I thank Professor Bhavir to share time. Thank you.
So just one comment. There is Moti who asked his question on the chat. Can I?
Oh yes, there is one more question on the chat. Yes, should I read?
Yeah, maybe I can just read a part. So the question is, if we change an n-dimensional vector by just changing one component, we will have a nearest neighbor at an arbitrarily small distance. Okay. And indeed, if you take your vector in high dimension and you just change one component, you will have another point which is very close, right? This is true, Moti, but the fact that you should imagine that these points are kind of sampled. What I was saying was true when you sample these points uniformly. So the probability that you change only one component by a small amount is extremely small, right? It's exponentially small in the dimension. So the event that you're talking about here will never happen. Of course, in real data, points, again, are not sampled uniformly in the space. You have structure, but at the same time, you always have noise, right? So you have some level of corruptions. And in high dimension, even a small amount of noise can separate a lot any 2 points. So what I was saying remains true, even if the data is structured due to noise, okay? It never happens that you sample a point which is very close to one by just changing one component. Okay?
Thank you, sir.
You're welcome. So see you for the next lecture on information theory. Bye-bye.
Okay, thank you. Thank you, everyone. So when we disconnect, we will join at 2:40, in 1.5 hours. After 1.5 hours. Chalo.